Hello, today we will continue our discussion of dynamics of microscopic systems by looking at the Schrödinger's equation. Erwin Schrödinger in 1926 proposed an equation to find the main function of any system. Here we have the time-independent Schrödinger equation. All you need to know about this equation without diving into the nitty and gritty parts of quantum mechanics is that it has two portions, the portion of potential energy and the contributing part of the kinetic energy. So the time-independent Schrödinger equation is of a particle m moving in one dimension with energy E in a system that does not change with time. For example, volume remains the same. If volume or pressure or anything changes throughout this process, there is nothing we can definitively say about the system. So, as you can see, the kinetic energy of a particle is proportional to h bar, and h bar is basically the Planck's constant divided by 2 pi. So it's quantization of angular momentum. So, and this comes in important, well, in a few slides, and you'll see. Now, we can solve this equation for many different systems, a number of important cases, but in this particular course, in which we're more interested in chemical physics, we will look at it from a perspective of quantization of energy. So, without going through the solving the differential equation yields the following result, in which phi equals cosine kx. K in this case is a square root of 2m times total energy minus potential energy divided by h bar squared. Okay. Now, here is what's important, what's interesting. Now we know that the cosine kx is actually it's a wave of wavelength 2 pi divided by k. Okay. In addition, energy minus total energy minus potential energy is obviously the kinetic energy, right? So this equation can be rewritten as this, that K equals square root of 2m kinetic energy divided by h bar squared, which then basically implies that the kinetic energy, right, equals to k square h bar squared divided by 2m. Okay. Now, this is also very interesting, and if you do not remember, well, we'll talk about it, I suppose. The kinetic energy, therefore, equals to momentum p squared divided by 2m. Now, why? Why? Because kinetic energy equals, obviously, mv squared divided by 2, right? We remember that. And we know that p momentum equals mv, right? We know that. So, therefore, p squared equals m squared times v squared, right? No brainer there. And then we can say that m times v squared is p squared divided by m, right? So mv squared divided by 2 equals p squared divided by 2m. Why is this important? Well, let's look at it from the momentum perspective. So E equals p squared divided by 2m. From here, it follows that momentum equals k h bar. So the linear momentum of a wavelength of the wave function is related to the following. P equals 2 pi divided by lambda times h divided by 2 pi. 2 pi's go away, and what we have left is h divided by lambda. Now, let's rewrite this. Let's rewrite this here. Momentum equals h divided by lambda. What is this from the last presentation? You should remember this as de Broglie relation. De Broglie relation, right? Angular momentum, or the momentum equals h divided by lambda. Now this is important to understand. That's why I'd like to go over it again and clearly write this out. So we have our cosine kx, which we know is now a wave of wavelength lambda, is 2 pi divided by k. This comes from the solutions, okay, of the quantum mechanics. So we know this now. Now let's go back to the basic physics. Kinetic energy equals mv squared divided by 2. We also know that momentum equals mv, right? So then we can clearly say that p squared equals m squared times v squared. So mv squared, our mv squared is therefore p squared divided by m, right? So then we can say here that mv squared divided by 2, or our kinetic energy, equals to p squared divided by 2m. Oops, 2m. Okay? So remember, this is important because now let's go back to our solution for wavelength. Now we can say that this is the same as 2m kinetic energy divided by h bar squared, and this is all square root. So if we rearrange this, we have our kinetic energy equals k squared h bar squared divided by 2m. And now, because we know that kinetic energy is p squared divided by 2m, from here it naturally follows that momentum is k times h bar. Therefore, the linear momentum is related to the wavelength of a wave function by p equals 2 pi divided by lambda times Planck's constant divided by 2 pi. 2 pi go away. We have h divided by lambda, which is the Pauli relation. Pretty awesome, isn't it? A central principle of quantum mechanics is that the wave function contains all of the dynamic information about the system it describes. For our direct purposes, we're concerned about the location of a particle. So this interpretation of the wave function that pertains to the location of a particle was suggested by Max Born, who came up basically with an analog of the wave theory of light, which basically states that the square of amplitude of electromagnetic wave in a region is interpreted as its intensity. From the quantum perspective, this is basically a measure of the probability of finding a photon in a particular region. So Born's interpretation of wave function focuses on the square of the wave function, as we have already mentioned previously. But now let's look at it from another perspective. In basic terms, Born interpretation states that if the wave function of a particular particle has a value of phi at some given point x, then the probability of finding the particle between x and x plus dx is proportional to the square of phi times dx. Therefore, the phi squared is the probability density, whereas the phi only is the probability amplitude. Now let's look at an example of a particle that is free to move in 3 dimensions, such as an electron near its nucleus. Then in that case, the wave function depends on a point r with coordinates that are x, y, and z. So in this context, the interpretation of the phi r in this case, the wave function of r, is that if the wave function of a particle has a value phi at some point r, then the probability of finding the particle in an infinitely small volume of dx, dy, dz is proportional to delta tau. Delta tau being the dy, well, let's say as dx times dy times dz. So for practical purposes, whether we're talking about it in one dimension or in 3 dimensions, well, they are fundamentally different in terms of complexity, but from the theoretical perspective, they're not that much different. When we talk about the probability of finding a photon or a particle in a particular location using the wave function, the actual value, negative or complex, which is in this case, or positive, has no significant impact. It's the square of the wave function value that gives us the probability curve only. Later, obviously, we will see that the positive and negative regions of the wave function do have significant contribution, of course, because it can give rise to a possibility of constructive and destructive interference. We will talk about this shortly. But again, when we're talking about the probability of finding a photon in a particular location, is only given by the square of the wave function. Now, the Bohr interpretation does put some restrictions on the acceptability of wave function. One of this is that the wave function must not be infinite over a finite region. If it was infinite, obviously it would not have been square integratable, and normalization constant would be 0. The Schrödinger's equation itself also has some mathematical restrictions. It is a second-order differential equation. As such, the second derivative of wave function must be well defined. If the equation is to be applied everywhere. And we can take the second derivative of function only if it is continuous. Basically means there are no sharp steps in it. And if it's a first derivative, its slope is continuous. Now, in this graph, we have several examples in which we have unacceptable conditions because there is, in this case, lack of continuity. In B, we have the slope is discontinuous. The C is unacceptable because it has more than one value for every given point. And D is unacceptable because it has values in which the function is infinite. Having said this, there are cases in which has a potential energy has peculiar properties. Or rather, potential energy can allow several acceptable wave functions to exist when, for example, the energy can quickly rise abruptly to infinity. Well, in everyday life we don't see that, but there are cases in which on an atomic scale in accelerators that this is observed, and it allows for certain variations to be acceptable. But as a general rule of thumb, this picture right here, this well defines what is acceptable and what is not. So any function that would have anything that is just continuous and has a single value for every point it does not have a value in which it approaches infinity, then it is a satisfiable wave. And we will conclude with this slide, which illustrates the probability distribution corresponding to the wave function. And as you can see, we have cosine kx, and if you remember, our cosine kx was related to the wave. So just a refresher, cosine kx was related to wavelength divided that equals to 2 pi divided by k. Now, cosine kx is our wave function, and the intensity distribution therefore would be cosine square kx. And obviously, cosine squared does not have a negative complex contributor, so our intensity distribution is as follows, and all it is the probability of finding the photon in that particular region at any given time. Well, with this we will conclude today. Thank you, and we shall continue with talking about some of the principles of quantum theory. Thank you.